All right, so in this example, this is the second example where we're going through the entire process of linear programming. Not as significant of an impact as almost $1 million as the last one, but still some savings nonetheless with what we're going to try to figure out here. So this is a fundraiser for baseball, and when my kids were growing up, there was a lot of baseball and a lot of fundraising going on to raise money for different traveling expenses that the team would incur. And so what we're going to try to do is figure out what's going on here and use linear programming so that we can save as much money as possible. Um, so let's take a look at this. It says there are 12 players on the baseball team, and all 12 players will sell at least 20 items, or at most 20 items. So let's say you don't want your kids, going door to door in the neighborhood. You just want them to sell 20 things. And the two things that they're going to be selling is candy bars or suckers. So candy bars come in a case of 10 candy bars in a case, and suckers come in a case where there are 30 suckers in a case. So an entire case of candy bars cost you $5, and an entire case of suckers cost you $10. So you'd have to purchase those up front and then give them to the kids, and then the kids sell them for a certain price. So your team, though, only has $100 to spend. So you can buy a lot of the candy bars or a lot of the suckers or a mixture of the two, but you've only got $100 to purchase these candy bars and suckers with. And profit for each case of candy bars is $9, and for each case of the suckers, your profit is $22. And so what you want to do, you might be the team mom or the team dad or the manager of the team or something, and you want to figure out how many cases of each type, the candy bars or the suckers, should be purchased to maximize your profit. So our goal here is to maximize our profit. And so I'm going to write an objective function first. That's objective number one, and that's to come up with an equation for profit. Only in our last one, we were trying to minimize our cost. Here, we're going to try to maximize our profit. And how do we make a profit? Well, if we call the candy bars X's, so maybe I'll put that down here. X will be a case of candy bars. Y will be a case of the suckers. And so if I buy and I sell a case of the candy bars, profit is $9 for each case. So it's $9 for each case of the candy bars, plus each case of the suckers that I sell gives me a profit of $22. So it's going to be $22 for each case of the suckers. And this is my objective function. That's what I would do first. Get your objective, try to figure out what it is that you're trying to do, and write your objective function. Step two, again, is the constraints. And so how come we just can't buy a billion of the candy bars and a trillion of the suckers and just sell a whole bunch of them? And that's because we have some constraints. The first constraint that we have is that we only want our players to sell at most 20 items. And so we've got a total of 12 players. And so if each player sells 20 items, that's 12 times 20, which is 240 items. So we're limited. We're only going to buy 240 things. And for each case of the candy bars, we get 10 candy bars. And so I'm going to write an equation that is something like this. We get 10 items for each case of the candy bars that we purchase, plus each case of the suckers that we purchase gives us 30 items. So 10 items for each case for the candy bars, plus 30 items for each case of the suckers, and we're going to sell at most 20. And so that would be at most 240. And so these two would be less than or equal to 240 items altogether. So we just don't want our kids to sell more than that. So is what maybe our parents decided maybe at a meeting earlier. So anyway, that's the first constraint. So we're limited on the things that we're going to buy. Well, what else is limiting us? And that would be that we're only going to spend $100. So we're going to write an equation for the amount of money that we're going to spend. And so for each case of the suckers that we purchase, we're going to spend a total of $5 for each case of the candy bars. Sorry. So $5 for each case of the candy bars, plus we're going to spend $10 for each case of the suckers, and that has to be less than or equal to a total of $100. That's another constraint. So we're constrained on how much items we're going to sell, and another constraint is that we're only going to spend $100. Now, we do have this. We're only going to purchase positive numbers of candy bars and positive numbers of the suckers. And so y is greater than or equal to 0 and x is greater than or equal to 0, because we can't purchase negative cases of anything. So these are our constraints. Not quite as involved. There are only two equations with the other two as well, being x and y is greater than or equal to 0. So after we write the constraints, the next step is to graph our feasible region. And so that's what I'm going to do over here. Our feasible region is going to be somewhere in the first quadrant, and we know that because the x is greater than or equal to 0 and the y is greater than or equal to 0. And so I know I'm in the first quadrant here, and that's because of these two functions. But then I'm going to graph these two functions, and I'm going to do this the same way that we did them in the other example. I'm just going to make an x and y chart and plug in zeros. And so if I plug in 0 here for x, 10 times 0 is 0. 30 times what gives me 240, and that's 8. And so we have a point here at 0, 8. Here's 1, 2, 3, 4, 5, 6, 7, 8. And then if I let y be 0, then 30 times 0 is 0, and 10 times something gives me 240. Well, that's 24. So because that's a ways out there, I'm going to count by twos here. This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's going to be right here. And so if I were to graph this line, it would look something like this. And I want it to be less than or equal to 240. I could plug in the point 0, 0 to figure out where I'm shading. But if I plug in 0 here and 0 here, this is going to be 0, which is less than 240. So my feasible region is somewhere in this triangle so far. But then I'm going to graph this equation. And so with this equation, again, I'm going to make an x and y table of values here and plug in zeros. If x is 0, 5 times 0 is 0, and 10 times 10 is 100. And so there's going to be a point up here at 10. And then, if I let y be 0, then this is going to be 0, and 5 times 20 is 100. Well, that's this point right here. And so then I'm going to have, I'll try to do this in as straight as line as possible, I'm going to have this constraint. And if I plug in the point 0, 0, I'll get 0 is less than 100, and so now it's less than this graph. So my feasible region is the area bounded by those lines, and I'm in the first quadrant. So I'm in this area right here, and that's my feasible region. That's the third part to this. The fourth part then is to figure out what my intercepts are. And so I know, like this point, I'm going to call this A, I'm going to call this point here B, and I'll call this point here C. A is the point 0, 8. 0, 8. B, I should put A there. B is the point, well, I'm not sure yet. Let's do C. C is the point 20, 0. So this is kind of difficult because we want to figure out, if I were to graph these perfectly, I probably would have been able to figure out what B is. But let's say I don't know what B is exactly, and I want to figure out what are the coordinates of B. Well, it's where these two lines intersect each other. It's where these two lines here intersect each other, which is the solution to this system. So what I could do to figure out the coordinates for B is I could take this system, which is 10x plus 30y. I'm just going to say it's equal to 240. And the other equation is 5x plus 10y equals 100. And I want to find their intersection point, which is the solution to that system. Probably an easy way to do this is to take this bottom equation and multiply it times negative 2. That'll give me negative 10x minus 20y equals negative 200. And when I add these together, those are eliminated. 30 minus 20 is 10y, and that equals 40. Equals, yeah, 40. So when I divide by 10, I know that y is 4. And if y is 4, I can plug that into either one of these equations to figure out what x is, and x will be 12. And so I'm at the point 12, 4. Now, it doesn't look exactly like that on my graph. They should intersect right there. So one of my points was off a little bit, or one of my lines was probably not perfectly straight. But those are my vertices, and those are the numbers that I'm going to plug in to see which one would give me the maximum profit. So now I'm moving on to step 5. And step 5 is to plug these numbers in to see what profit they're going to give me if I sell all of those items. So I'm going to plug them into the objective function and figure out what my profit is. If I take point A, it's 9 times 0 plus 22 times 8, which is $176 profit. If I plug in point B, it's going to be 9 times 12 plus 22 times 4, which is $196 profit. And if I plug in point C, it's 9 times 20, which is $180 profit. And so if I want to be the very best team manager or team mom that I can be, then I'm going to purchase 12 of the candy bar cases and 4 of the sucker cases, because it'll give us a profit of $196 as opposed to $176 or $180. And you might be thinking, well, what's the big deal about that? Well, it could be that you're able to now maybe purchase like a batting helmet for each kid with an extra sticker on it. And that extra sticker might give them the confidence that they need to work a little bit harder and become a little bit better, which might give them the confidence to make their high school baseball team, which they might develop in high school and become a really good baseball player, get a college education paid for because they get a scholarship to play baseball in high school or in college, and maybe they're able to get a degree that they want to simply because you were able to do some linear programming and buy an extra sticker on their baseball helmet. And isn't that worth it for your kids? So anyway, this is how we would do the second example of linear programming, and I hope this makes sense, and we will do more of this when you come to class tomorrow. Have a good night.